Find the critical numbers in a function with rational exponents. The textbook definition is on screen, but pretty much it just means that for anything that is in the domain, anything that I can put into x in the original function and it's there, a critical number happens when either the first derivative at that same spot is a zero, like a max or a min, or the first derivative doesn't exist, like an asymptote. Here's your original function. I'm going to look at it because why would I not look at it? So in a TI-84, I'm going to use x's and y's, and in Desmos, I'm going to use f of x's and x's. So right here, this would be x to the 3/4 power minus 2 x raised to the 1/4 power. And then take a look at that graph. What does it look like? So I can kind of see where the bumpy parts are. Bumpy parts right here, something kind of weird going on right here. I have a good idea where I'm going with this. This time showing Desmos on screen. This is where you go for Desmos if this is new to you. Type it in as an f of x, that's really useful, instead of a y. Now what I want you to do is take the first derivative, using the power rule, using all the things you know about calculus already. Verify that when you take the first derivative, you get the same thing that I got on screen. So I'm going to pause and look at it. I'll go to y equals, and I will type in, you don't have to do it the fancy way, 3/4 x raised to the negative 1/4 power minus 1/2 x raised to the negative 3/4 power. And then look at it. So on my TI-84, the derivative is showing up as red. Notice also in Desmos, which is also on screen, that my derivative is showing up in blue, and all I had to do was type f prime of x. That's why we bothered to write f of x instead of y the first time with Desmos. And we'll just graph it for you. Now you're still going to have to show your work on paper. But look at the important things here. So you see how might have some interesting stuff going on right here. Might have some interesting stuff where it crosses over the x-axis. These are going to be the things that we're looking for. So do this mindfully. You have pictures to look at to help you make inferences. That's the reason we taught you to graph, so that you could make the inferences. This next part is often the hardest part, and it's factoring, but it's factoring with rational exponents. So this would have been taught in college algebra, but you would have seen it once or twice. It hinges on the idea that you learned in an earlier algebra class. So here are a couple things that we're doing. Do you remember from a long time ago, whenever you're trying to take out a GCF, we would say, whichever one is the smaller exponent? Well, the smaller exponent here is negative 3/4. So I'm going to factor out t to the negative 3/4. When I factor it out, I'm going to subtract a negative 3/4 from each of my exponents. So you're going to see a 1/2 in there. You see in my factored part, there's a 3t to the 1/2 power. That comes from the t to the negative 1/4 minus a negative 3/4. So it's going to come out like t to the negative 1/4 plus 3/4, and that's where that 1/2 is coming from. It would be 2/4, which simplifies to 1/2. The reason we're doing this is because if I always factor out what my smaller exponent is, and you see it's a smaller exponent because it's farther to the right on the number line, then I always end up with positive exponents inside. This is my preference. It does not mean it's the gospel truth in this way. You have to do it. The other thing that I did is I got rid of my denominator nonsense by factoring out a 1/4 as a coefficient. So I looked at my two denominators. I have a denominator of 4 in the 3/4 t, and I have another denominator of 2 in the negative 1/2 t or minus 1/2 t. And so since both of my denominators are factors of 4, I factored out a 1/4. Now because I factored out a 1/4, the 3/4 had it, and the 1/2 was only a 1/2. That's why I have a minus 2 right there. This is some fancy factoring. It is my opinion. of the easiest way to get to my next steps. So I'm factoring out my least common denominator as a 1/4. And I'm also factoring out t raised to whatever the smaller exponent is. And my smaller exponent is -3/4. Then we're going to set the factors of the derivative equal to 0. I implore you should probably look at the pictures too. Then we're going to set our individual factors equal to 0 and solve algebraically. Left bound. Picking somewhere where the y is negative. Picking somewhere where the y is positive. Fascinating. You should be solving algebraically. Also, you should use your tools to verify your answers. And that way, you feel much more confident. Let's take a look at that negative exponent for a second. Let's move it down to a denominator. You have 1/4t raised to the +3/4 power. And that's supposed to equal 0. Is there any way to have something where all of your inputs are going to be positive t values? You have 1/4 times something positive. Is there any way that you're ever going to get to 0 with that? No. So, something's fishy with that one. So we're going to say very confidently that the first derivative is not going to exist right there. So we're looking for some sort of asymptote going on right here. Everything that you've ever learned about undefines, all of that. Asymptotes, so that the first derivative at 0 doesn't exist. Well, let's move on to the other one and add 2 to both sides. Concerning that other factor that we set equal to 0, we've already added 2 to both sides. The next thing we're going to do is divide both sides by 3. And here we are at t to the 1/2 power is equal to 2/3. So now we need to get rid of that exponent of 1/2 because we're trying to solve for t, not t to the 1/2. So I'm going to square both sides. That way, the 1/2 goes away. Now let's verify that our answers make sense according to the function. I'm going to use a TI-84 first. Now I went to second and graph to get to the table. If there's anything in here, if it's 1, 2, 3, 4, 5, it means that we need to change our table settings. So second and window will take you to table setup. Independent needs to be on ask. And if you had a whole bunch of other numbers in there and you already had independent on ask, it means you just need to delete these. Anyway, so we're going to put in the 2 things that we found. First of all, if a monomial is supposed to be equal to 0, then I'm going to put in a 0, enter, and the other one that we got was 4/9 on screen, so 4/9, because that is 2/3 squared. Now our definition says that f of c, the values have to exist in the original function. Our original function is in that y sub 1 right here. So see how both of these things exist, and when I take the first derivative, that's in y2. Either it doesn't exist, like this one, or the first derivative is equal to 0, like this one. So these are our 2 critical numbers right here, because they exist in the original ones. When we solved for these things in our first derivative, then they exist in the original, and then our second derivative, I got an error for one of them, and I got a 0 for the other one. So those fit our original definitions. In order to verify your answers in Desmos, there are a couple things we could do. First of all, right here, when I'm here, I can click this little icon and label it, and stuff like that. But another thing I'm going to do, just because I want tables, I'm going to go here. I'm going to backspace out of anything that I don't want because I really only needed 2 points for the sake of space. The 2 input values that I'm concerned about It says x on screen, but it's t in the problem, are 0 and 4/9. And then I come over here, tell my derivative that I also want a table. Zero and 4/9. So the nice thing here is it will show on screen. You can do this, you can do this. So, and my original function has to be defined at the numbers we found. They are defined at the numbers we found. But furthermore, then our first derivative at those values has to be either undefined, or it has to not exist, or it has to be 0. And this makes sense. Right here, where x is 0, this is kind of critical. And then right here is a minimum, so that's why this one's a 0. Here's our original function. It's important to the shape of the graph that the first derivative doesn't exist right here. See, the first derivative doesn't exist right there. And this minimum right here is where the first derivative is 0. In conclusion, by no means am I suggesting that you don't know the calculus and just use a machine instead, because if you only know a machine and you don't know the calculus, you're not going to get there anyway. Consider all the things that I have needed to input into a machine after doing some calculus. So you need to know the definition of a critical number here. You need to know how to take a first derivative. You need to know how to factor. These are all things that we're advocating for. But also, the graphs help you make inferences. Like right here, here's a minimum value, and its first derivative is 0 right there. These are tools to help you learn things. So, well, I just want to know the calculus, and how would using a machine help me in the real world? You are going to verify all of your results in the real world anyway. So use everything that you can to help you learn and to make inferences and learn the calculus and recognize the factoring. But when you need to verify that what you did was good, look at pictures, because they should coincide with everything that you've already done. This isn't cheating. It is part of a process. It's good times. It's a valid way to get there. Anyway, happy calculusing.